In this video, we'll cover the problem word ladder. So you'll see we're defining a transformation sequence that starts with begin word and ends with end word. It's basically a sequence of words starting from begin word, going to another word, another word, another word, so that every adjacent pair of words differ by one letter, and each of the words in our list is part of word list. We'll see some examples which I think will clarify what exactly this notation means. And then lastly, the last string must be the end word. So before we even look at the problem statement, let's understand what that's stating. Here is an example, and I think examples tend to make this kind of notation a lot more concrete. So here, our begin word is the word hit, and our end word is the word cog. Now you can see we go from hit, and we change one letter. So then we get hot, and hot is in our word list. These are kind of our valid words, our acceptable words. Then from hot, we change one letter to get dot, which is also in our valid words. From dot, we change one letter to get dog, dog, which is also in our valid words. From dog, we change one letter to get cog, which is also in our valid words. So you can see that basically what we're saying is start at an initial word, change one letter at a time, but make sure that every time you change a letter, the new string is in our valid words. Then you basically want to continuously do this until you get the end word or our target word. And our task is to return the number of words in the shortest transformation sequence from begin word to end word, or we return 0 if no sequence exists. So in this case, we have 1, 2, 3, 4, 5. So we return 5 in this case, and that seems right. All right. Now the first thing I want to mention is you can see that we have a bunch of pieces of information, words that are we have relationships to each other. Certain words are related to other words, and we can model this as a graph. So we have a hidden or implicit graph in this problem. Our nodes are our states, our pieces of information. And our states in this problem are words, so each word. For example, hot or dog are nodes. Now, what are our neighbors / edges? These are related concepts. Well, neighbors are all of the words that are related to the current word. So all words that can be formed by changing one character of a node's word. So for example, hot has neighbors. We could change the H to an A. We could have AOT. We could have BOT. We could have COT. ... We also could be changing the O, so we could have HAT, HBT, HCT, and that continues. And then obviously we can also change HOA. We can change that third character. We can have HOB, and so on. So that's what our nodes and our neighbors are. One other note is whether or not this is an undirected graph. Well, if we can change HOT to AOT, so HOT can go to AOT, but also AOT can go to HOT because we just changed the A back to an H. So this is an undirected graph. As we've seen many times now, that will be important because of the fact that we are going to have to worry about cycles because we have an undirected graph. And undirected graphs can have cycles, meaning we need to handle some visited sets. Now, there is one other point we should actually clarify here, which is that neighbors are, this part is true, they need to be able to be formed by changing one character of the current node's word, and the resulting string is in our valid words. So here, this is assuming that all these neighbors are also in word list. So for example, if in this case, actually we can actually write this with example 1, HIT has these neighbors. HOT, we can definitely form that with one change, and it's in our valid neighbors. And Actually, looks like that's it. That's the only one. Because it's the only string that's formed by changing one of these letters, and the resulting string after changing one of those letters is in our word list. We can also, well, we'll do one more just to be a little bit more explicit. So HOT has DOT as a neighbor, it has LOT as a neighbor, and it looks like that's all. Yeah, because these are the only strings that are in word list that also have a one-letter difference that is valid. Okay, great. So we've defined the graph here, and we have a good idea of what's going on in terms of how we're representing this information. Now, this problem is basically saying we have a graph, which is a bunch of nodes and edges between these nodes. We have some start node, which is our begin word. We have some end node, or some target node, which is our end word. And we basically want to find the length of the shortest path between our start node and our end node. We know how to do that. We can use a breadth-first search, and that is going to allow us to go level by level, starting from our initial node and kind of traverse outwards, such that the very first time we hit a node, we have found the shortest path to that node. Now, quickly, I forgot to do this in the beginning, but I have these two helper functions here that will just convert a char into its ASCII value, and will take an ASCII value and return the char. These are going to be helpful for us, and these are kind of Googleable. You can just look up JavaScript, how to get ASCII value of char, and how to get char from ASCII value. Just wanted to paste those before I accidentally copied something else and lost them on my clipboard. Okay, yeah, so we're going to be doing our breadth-first search, typical way to get shortest path between two nodes in a graph, whether it's directed or undirected. All right, now here, okay, we can go ahead and get started coding our algorithm. The main tricky piece here is going to be getting neighbors. Like, given some string, how do we kind of generate all of the strings that are neighbors of that string? The first thing we'll do is I'm going to create a set called valid words so that we can check if something is a valid word in O of one time. And that's just derived from our word list. Now, one thing I want to mention is if valid words does not contain the end word, I'm actually going to rename it to be the target word. Begin word, end word. End word is fine. If it does not contain the end word, then we can already return. What do we want to return? In this case, it's not actually possible to construct a sequence, so we should be returning 0. And let's define a constant for that. So we'll say no sequence exists, or no valid sequence exists. It's going to be 0, and we will return that number, that constant here. Otherwise, we'll do get shortest sequence length. Just have a function here that's going to execute our BFS logic. It'll need the begin word, it'll need the end word, and it's going to need our valid words here. Okay, now we're going to write our breadth-first search. So we'll come here, we'll define our function. It's going to take in a begin word, an end word, and valid words. Now, we're going to define our queue, so we'll do that the way we always do it. We're going to make a new queue. We're going to want to add our start node to the queue. Now, we want to source the metadata here, as we always do when we write our BFS to find shortest paths. So we're going to store the word, which will be, initially, it's going to be our begin word. And we also want to store num words in, well, it's like the number of words in the sequence so far. So how can we write that concisely, or somewhat concisely? Num words in sequence. In cur sequence? Yeah, we can do that. Num words in cur sequence. Yeah, that's all right. And it's going to start off as 1, because we already have one word in the sequence that just contains this. Be careful with when you're defining 1 versus 0. It depends on whether or not you're counting edges or nodes. And in this case, we're counting nodes, so we start with 1. Now, also around this time, you want to be thinking about, should I be tracking visited information? Which is basically asking the question, can this graph have cycles? This one can, as we discussed before, it's an undirected graph. So we must have a visited set. So we'll create our visited set here. Now we can do our standard BFS logic. So we're going to create our while loop. We'll have our 3 steps: remove node, process node, and add neighbors. At the remove node step, we're going to add or destructure out our word and our num words in cur sequence just by doing q.deq. Process node will come back to that. And for neighbors, what we can do is we'll say neighbors equals get neighbors. We'll kind of put that in a function, because as we know, that's going to be a little complicated for this problem. That's going to take in the current word, and it's going to take in valid words as well. Then we can say for each neighbor of our neighbors, what are we going to do? Well, if it's visited, we don't want to add it to the queue. So we can say a visited.has the neighbor. And so to be clear, we're going to have neighbors be an array of strings. So if visited already has this string, we can continue. No need to add it to the queue. We could here do some check that's like, if the neighbor is not invalid words, then do not add it to the queue. However, with the way our graph is defined, these guys are only neighbors if they are invalid words. So what we're going to do is we're going to check that they're valid words in our getNeighbors function. That's why I'm passing valid words. So at this point, anything that is included in neighbors is a real neighbor in our graph, meaning it is a valid word. So we don't have to do that check. Then we'll just add our neighbor to the queue. Okay, so this is the skeleton of our BFS. We also can handle the case where we do all of our logic and we never find our desired end node. We never found a path. And that means that no sequence exists. So we'll return no valid sequence exists if we continue and break out of our while loop without ever returning. Now, of course, we want to handle the process node step. So that answers the question of what do we want to do at each node? Well, at each node, we want to mark it as visited for sure. We know it's unvisited right now because of this, but we should say, hey, I visited this node now. But also, we want to check and see if we've reached our end word. If we have reached our end word, we can go ahead and return our answer. So we'll say if word is equal to end word, return num words in cur sequence. And because this is a BFS, we know that the first time we ever hit this line being true, we have the shortest num words in cur sequence. All right, I believe that should be everything for this core function here. Now, let's write out our getNeighbors function. It's going to take in a word and valid words. Now, what do we want to do here? Basically, we want to take some string like this. We want to go through every position, and then at each position, we want to try replacing that character. So if we try to replace this O with A through Z, everything in A through Z. Yeah, and we don't even have to worry about like if we're creating a string that's duplicated because we're going to check visited nodes, so that should be totally fine. So here's what we'll do. We will say neighbors is going to be an array. We will say return neighbors. Neighbors. We're going to iterate over our word. So we'll say I0, I less than word dot length, I plus plus. You know what? I made a mistake here. Here, when we're adding the neighbor to our queue, we should not be adding the neighbor to our queue because we've defined our queue to contain objects. So we actually want to create an object as word, which is neighbor, and then it has num words in cur sequence, which is going to be num words in cur sequence plus 1. The reason is we've just added this neighbor to our sequence, so we need to account for that when we're counting our sequence length. We want to make sure that our data type is consistent, and when you're using objects in the queue, you need to be careful to make sure that you're consistent in doing that everywhere in your program. Okay, sorry about that. Back to this point. So we're going to iterate over every character in our word length. Now, we can say, we can get, let's see, we can say substring before I is going to be word.substring 0, I, because I is exclusive, the second boundary. And then we can do substring after. I is going to be word.substring, I plus 1. And then as a default, that'll go to the end of our string. Now what we can do is we probably want some function that's going to try everything from A through Z. So what we'll do here is we'll say all one diff words. That's what I'm going to call it. It's going to be get all one diff words. I'm calling them one diff words because they have one difference, right? Only one character is distinct if you compare this word and the new word. And we're going to pass in the substring before I and the substring after I. Now, so this will give us an array that's like a bunch of strings or words that have one difference. Now we only want to add the ones that are valid, so we can say for const all one diff word of all one diff words, if valid, or if it's not invalid words, so if not valid words dot has the one diff word, continue. Otherwise, it's a neighbor. If it is invalid words, then we're good to go, and we can add this one diff word as a neighbor in our neighbors array before we return. Okay, great. Yeah, let's go ahead and implement our method here. So this is going to be get all one diff words. It'll take, actually I'm just going to copy this part. So it takes the substring before I and the substring after I. Now, we want to iterate from A through Z. So here's what we can do. We can say let char num, we're going to use ASCII values. So we're going to get the ASCII value of the string A, and we'll do char num less than or equal to, and we'll get the ASCII value of the string Z. And then we'll just do char num plus plus. And so this is going to iterate over the ASCII value for A up for the ASCII value for Z. We could also make these constants. I think in this case it's kind of up to personal preference. I'll go ahead and make one for lowercase a. It's going to be A, and we'll have lowercase z, which is Z. And for this problem, I believe we can assume that we are only working with lowercase English letters. Okay, so we can replace these hard-coded strings with our constants. Yeah, and this is, in this case, I think it is also okay to not use the constants. It's kind of up to whoever's writing the code. We also should make sure that we have a one diff, or all one diff words array that we can return in the end. Now, when we're iterating through A through Z, we're going to say char is going to be get char, and that's going to use this method I wrote here, or this function I wrote here. It's going to take in our char num, and that gives us the char. Now, the word is going to be, or we can call it a one diff word, is going to be the substring before I plus char plus substring after I. And then we can simply add it to our all one diff words. And we don't even need to check if it's valid because we are already checking that right here. So we can simply push the one diff word right here. Okay, I believe this should cover our core logic. Most of kind of from here downwards is standard BFS type logic. Here, to get a neighbor, we're just saying, look at each position. For each position, we're going to consider substituting out that position, meaning we grab everything before it, everything after it, and those stay the same. And we try every character A through Z at that position. And so that's what's happening right here. Then, for all of those kind of one diff words, those words that have exactly one difference, we check if they're valid. If they're not valid, we ignore them. If they are a valid word, we push them to our neighbors array. So that way, neighbors should contain all of the one diff words that are also in our valid words set. So hopefully this is what we want. Let's go ahead and see. Looks like I wrote neighbor.push instead of neighbors. Okay, looks like it passes this case, and let's see what happens when we submit. Okay, looks like it passes on the submission as well. All right, well, that's all for this video, and thank you for watching.